Okay, year 11, I'm going to go through the next exercise 905, the product rule of probability. Now, we did do this last year, but I want to go over quickly some things that we need to make sure we understand. So, the first thing you need to know is the fundamental counting principle. And we did it last year, but the fundamental counting principle is to multiply. And this gives us an understanding of how to work out the sample space. And it'll lead us into this product rule. So make sure somewhere you've got the fundamental counting principle. And I'll give you a quick example of it. So if three people were to line up in a line, I don't want to do that one. If we did tossing two coins. So when we toss two coins, when we toss the first coin, there are two things that can happen. And when we toss the second coin, there are still two things that can happen. And it doesn't matter if you toss the coins at the same time or if you toss them one after the other. The same probability applies. And let's go one more time. Let's toss a coin or toss three coins. Now, if I were to do this as a tree diagram, which you can see down here, they've already started, two coins. When I toss the first coin, I can get a head or a tail. When I toss the second coin, I can get a head or a tail. And if I got a head or a tail on the first one, that'll give me four options. There are two here, and I multiply by two, and I get four. And these are the four options. And if I toss them yet again, or toss a coin again, or toss three coins together, I will get all these options that can happen. And the fundamental counting principle just makes you understand, well, how many things are going to happen? Now, I could write all these out, like a head, and a head, a head, and a tail, a head, a tail, and a head, a head, a tail, and a tail, a tail, a head, and a head, a tail, a head, and a tail, tail, head, and tail, tail. And there are 8. And the fundamental counting principle, 2 times 2 times 2 gives me 8. So the fundamental counting principle just means that you're going to multiply. And a tree diagram is just a way of getting your list. So if I go back to that other situation of some, three people in a line. So let's call the people A, B, and C. So if I make a list of these people, well, A can come first, and then I can have B and C. Well, A can come first, and then I can have C and B. They're the only two ways that I can have A come first. And intuitively, you should be thinking, all right, but there are two other people, or there are three people that can be first. So it should be 3 times 2, which it is, 6, but there's also going to be a 1 there because if we had started with one person in a line, A, there's only one way. With two people in the line, we can have AB or BA, which is 2, or 2 times 1, because there's two people who can be at the front. And then we just keep going. So 3 people in a line, which we've just done, and we all know, or we should know, that that's 3 factorial. So the fundamental counting principle applies to helping us find the sample space. Now, so for example, when I roll 2 dice, there are 36 things that can happen, and you really need to be able to do this. If you haven't got it, stop the video, make sure you have that. A two-way table is a very good way for establishing all the different things that can happen when you have two things. You can't make a two-way table, for 3 things. The other thing which you really need to write down is this. And I'm going to give you a question when we come back to school that was in one of the trial papers that stumped us for a while. and this is important, if A and B are independent events, then A occurring does not affect the probability of B occurring. The probability of both occurring is a product of their probabilities. The probability of A, and I like to use this word, and, because it includes everything, the probability of A and B, or you multiply. And it all comes from the fundamental counting principle, tree diagrams, making lists. Once you understand that, you don't actually have to make the list. And I'll show you why, and I'll show you how it works. So we're only doing the even questions in this exercise, but I'm going to do the first one. Now, if I'm tossing two coins, and I've already done the tree diagram for it, but I'm going to do it again, I can get a head or a tail, a head or a tail, or a head or a tail. Now, there are four things that can happen. A head and a head, a head and a tail and a head, a tail and a tail, and these are all even or equally likely probabilities. So each arm has a half on it, or the chance of each thing happening is a half. And you just multiply those. Now, I don't want to go and draw that every time, and you do not need to. So the probability of getting two heads, well, you just write it like this, the probability of a head and a head. And you go, well, what's the probability of the first head? Well, 1 on 2. Product rule, we need a head and a head, multiply. What's probably getting a head on the second go? Oh, 1 on 2. That gives me 1 on 4, which is that out of 4 things. Now, let's have a look at number 2. I don't need to draw it. I could just draw the arm that contains it. So I can get a head and a tail, a head and a tail. I don't need to write all the different things that can happen. I just need to follow this. Oh, come on. This branch. I'm hoping this colour comes up straight away. And that's what I'm doing when I do the product rule. I'm just taking that arm, those branches of that tree diagram. So the probability of a head and a head and a head, 1 on 2 times 1 on 2 times 1 on 2 equals 1 on 8. I don't need the whole tree diagram. In fact, I don't need the tree diagram at all, but the tree diagram is a good way to making sure sometimes you don't miss things because they can get a bit harder. I'm going to let you keep going with these. It's not that hard, but I'm going to skip down. I'll have a look at question 6. So the probability of a certain plant flowering is 93%. If it has 3 of those plants, that they will all flower. I'm not even going to write this out. So the probability of flowering and flowering and flowering, well, that's 93 on 100 times 93 on 100 times 93 on 100. Fairly easy stuff. It's not difficult. By the way, I just looked at the answers. They've got the same working. That becomes 80.4%. So let's get a bit harder. So I'm going to cruise down here. Let's have a look at question 10. So we're playing Yahtzee. Yahtzee is a game where you roll 5 dice and you count the number of different groups you can get. Like you get how many ones, how many twos, the most number of sixes, you can, all sorts of different things. So if I roll 5 dice, well, how many things can happen? 6 times 6 times 6 times 6 times 6. 1, 2, 3. That's how many things it can happen. And that's 7,776. There's 7,776 different things that can happen when I roll 5 dice. So what's the probability of 5 sixes? Well, the probability of 5 sixes, 6, 6, 6, 6, 6, is 1 on 6 times 1 on 6 times 1 on 6 times 1 on 6 times 1 on 6, which is 1 on 7, 7, 7, 6. Pretty basic. No sixes. Now here's where you've got to be smart. If you're not going to get any sixes, well, that's a probability of no, 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 and no, which will be 5 on 6 times 5 on 6 times 5 on 6 times 5 on 6 times 5 on 6, which is 3125 on 7, 7, 7, 6. Now this is my favourite one, the at least rule. At least 1 6. Now I could go and draw the tree diagram, and I can draw the tree diagram just for sixes. I don't have to draw everything. So imagine, here's my tree diagram. I'm going to do this 5 times. I can get a 6 or not a 6. I'm not going to draw this whole thing. I can get a 6 or not a 6. I can get a 6 or not a 6. That's going to be 2 to the power of 5. And that's, what's that? 2 to the power of 3 is 8, 16, 4, 5, 32. I'm going to have 32 different things. I don't want to draw all of them. But in all but one of these, I will get a 6. In every other thing that happens up here, there'll be a 6 in there. The only thing that has no 6s is that. So the probability of at least 1 is 1 minus the probability of none. Now you need to write that somewhere because you need to have that. It saves a lot of work. Because what you can do then is you can just work out the probability of this, and all the things up here plus this thing must add up to 1. So if I go 1 minus this thing here, I get all of those. So the probability of at least 1 equals 1 minus the probability of not a 6, 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 which we already worked out. 1 minus 3, 1, 2, 5 over 7, 7, 7, 6. 4,651 over 7, 7, 6. All right, you have a go at questions. Come on, please don't go all the way back to the beginning. It hasn't, good. You make sure, and I know I jumped into probability trees. You can have a go at those. I don't think there's any really hard ones. You have to be careful of replacement. 2 cards from a deck of cards, 18, 20. Find the probability of selecting 2 apples from fruit bowl that contains 9 apples. Okay, righto. They're all pretty good. Anyway, good luck with that, and we'll see how you've gone when we get back to class.